So the people at Beyond Horizon have written another TMUA paper. They call it Specimen Paper 1. So it's quite a nice paper. I thought I would do it, so thank you to them for writing that. Also, on their website, apparently you get a 20% discount if you use the code GOAT R2Drew2 on it, which is very funny. I've not been paid to say that, but I just thought it'd be funny to actually write that down. I want to be very clear, I've never been paid to say anything on this channel, and that will continue to be the case for all those people who send me sponsorship things. Unless you put a code in it that says GOAT R2Drew2, I'm probably not going to mention you at all. Um, anyway, good. Question number one. So x is a positive integer multiple of 12 I mean, that's 400 and that's 441. You should probably just know that to save yourself some time. I mean, 420, I think, is a multiple of 12 because of, 120, 240 in 200s, I guess. So yeah, 420 is the obvious one to use. There are 40 things in there. So if you go back 12 and forwards 12, I think 408 and 432 are going to be the ones. So yeah, 420 is the standard, is the starting point, and then you can just go back and forwards. I think there are three of them in that range. So yeah, cool. This is just one of those last digit questions. So we can see the minuses here. So let's just do the first bit. 6 times 2 is 12, so that ends in a 2. Times 4 is 8, so all of this ends in an 8. Times 7 is 56, so all of this ends in a 6. And then times 8 would get you to an 8, I think. So all of that ends in an 8. And then we're taking away 1 times 7 is 7, times 4 is 28, so that ends in an 8. Times 6 is what? 48, so that ends in an 8 as well. Times 8 is 64, so that ends in a 4. And then we're just going to do 8 to take away 4, and it will end in a 4 as well. Yeah, so yeah, just the last digit problem. Of course, I mean, if you're good, if you've done math challenges, you know that you're not supposed to actually do maths, right? You always look for tricks. Question three, I think I've done it in a really stupid way. I essentially just threw in the bounds each time. So like 1 over 1 minus 1.5 is 1 over minus 0.5, which is like minus 2. And then if you put in 2, you just get minus 1. So that means x is between those two things. Um, you can verify as well if you want to be super safe that if you put in like 1 3/4, you end up in between the two things. It's possible that there was a discontinuity in between the two, which I didn't actually check, but it's actually not possible, right? Because the discontinuity happens x equals 1, which is not in this range. So I think this method actually does work, come to think of it. So yeah, okay, fine. So we can continue with this. We're going to put in this and this into here, and we get that. Of course, this means that this is larger than this function in this range because this goes up to minus a third, whereas this one only went up to minus 1. And I'm just going to continue this method over and over again. And this one ends up being the largest here. You actually also don't need to check the bottom bit because, as we said, all we're really checking is how big it can possibly get. And this is the one that can get the largest. So I think D is therefore the answer. So that question, very inelegant way of doing that question. I'm sure people in the comments will point out better ways of doing it. Anyway, this translation is 3 across, 1 down. So that's going to be x is replaced with x minus 3 because we're going right? So it's minus 3. And then we're going to minus 1 at the very end. Reflection in the y-axis is when you just replace x with minus x. So that makes this. Now, of course, when you square this, because it's all negative, it's the same as squaring that. So we can just put that down. Then we stretch parallel to the x-axis, scale factor 5, and that's going to be f of a fifth x, I believe. So just replace x with a fifth of x, and then we just expand out. There's really nothing interesting about this. We just expand, and it turns out that one of those answers is the answer, and we are good to go. I factorized out a 3 from all of these terms to get this on this question. Now, there are 81 numbers between 20 and 100, because 21 to 100 is 80 numbers, I think, and then you've got essentially the 0th number is the 20th. So there's 81 of those. So it's going to be 81 root x plus whatever 20 plus 21 plus and so on to 100 is. Now, we should know that 1 plus 2 plus 3 plus and so on to n is n into n plus 1 over 2. It's just the triangle sum formula. So to sum the numbers from 20 to 100, let's just sum the numbers from 1 to 100 by doing 100 times 101 divided by 2, and then take away the numbers from 1 to 19 by doing 19 times 20 over 2. Of course, that's just 190 because 20 over 2 is 10, and this is just 50 times this, which is 5050. And then, of course, we can times the whole thing by 3 because of this factorized 3 on the outside. Now, that means that a over 3 is this thing here. So if we just divide both sides by 3, that gets rid of this times by 3. So we end up with a over 3 is just this thing here if this was a, right? So we end up with this. This here is just that. Now, a over 3 has to be a perfect square. So what I did was I just looked for perfect squares near this number. Now, the obvious one is 70 squared because of that, right? So then I said, well, okay, the difference between those two things is 40. But like 40 divided by 81 is not a nice number at all if I then try and solve this, right? Like essentially I'm just setting a over 3 to be 4,900. and this doesn't work. So the next square is this, and again, take away this from both sides, and you end up with 181, which again doesn't divide by 81 nicely. Next one is this, and that actually does work. When you take away this number, you get 324, which is square, but that actually doesn't matter. Dividing by 81, though, is the interesting bit. That makes exactly 4. So therefore, root x needs to be 4, which means x is 16, will totally work. And yeah, so bit of trial and error there at the end, which isn't too nice, but whatever. Whenever I see questions like this, I always just make up numbers. So 1 kilometer track, let's just pretend that it took RT, which is this person, round T. Let's just pretend it took him 1,000 seconds, which means, of course, he was going at 1 meter per second. Now, that means if he finishes lap 200 meters ahead of Big M, that means Big M did 800 meters in that same 1,000 seconds. So 800 over 1,000 means his speed was 0.8 meters per second, which means we can use that speed, using distance over time, of course, to work out how long it would have taken him to do the entire thing at a speed of 0.8 or 4/5 meters per second. So his speed is 4/5. His time is, I think, what I want to find out. Distance, of course, is 1,000. Let's do 1,000 divided by the 4/5, which is the same as 1,000 times 5/4, which is 5,000 over 4 seconds. So that's how long he took to do the entire race. And then we just repeat the process. So he finished 200 ahead of Lucky L. So, of course, what we can say is Lucky L's speed, given that they did 800 meters in this time, because they were 200 meters short of the finish line when this person finished, we can say their 800 divided by 5,000 over 4 makes this, again, some KFC gets that pretty quickly, and then some cancelling down for this decimal is also not that hard, or multiplying up for the decimal, actually, is easier. But you get this decimal as their speed, so then we work out how long they took to do the race. This is, again, a very inelegant way of doing this question. But if I do 1,000 divided by this speed, you end up with this, again, just some KFC I was very quickly doing on a notepad. And then one more time, we can say, well, okay, that means this KK person did 800 meters in this time, so divided by that. Again, some more KFC here gets you this. And then, of course, we can say, well, okay, when round T finishes his lap, well, that takes 1,000 seconds. If that's his speed, just do speed times 1,000 to get how far he had gone, which I think is 512. Yeah, again, another very inelegant way of doing that question, but yeah, this is just a quadratic. It's just u squared minus 2u minus 1 equals 0. It's very easy to solve very quickly. You get this. Now, u is cos of 2x, and of course, cos of 2x can't be bigger than or less than 1 or minus 1. So the only solution to this is 1 minus root 2. And then, of course, you can just cos inverse and halve, and then add the multiple to represent, moving along in the cos solutions. But I think that's only it. Now, minimum of a 1 over is the same as finding the maximum of just the thing on the bomb. So we're just looking for the maximum of this. I've rewritten it because, again, we can probably spot immediately this is just a quadratic. Because this is the same as 7 to the power x to the power 2, because then you could just multiply them for 2x. This is just u squared, and this is just u, and you can write it like this. And then, of course, we can complete the square and find that this is at its smallest at it says it's biggest at -3, because anything you put into u squares to make a positive, and then it's negative, so the biggest this can possibly be is -3, which means the smallest this can be is 1 over -3, which is -1/3, or -1 over 3, I guess, writing like that. You select 2 cards. What's the probability the cards don't have the same value? Well, okay, it's a probability tree. I thought I would actually draw it. And I'm not going to draw the entire thing, because, of course, this is just the 2 bit of the probability tree. So a 2, then a 2 is 1 over 13. There are 13 different things in a pack of cards, by the way, from ace to king, or from 2 to ace, depending on how you count. Anyway, 1 over 13, and then because you've already got rid of one of the 2s, there are only 3 left out of 51 cards. So we can times those together to get the probability of getting times these together to get the probability of getting a 2 and then not a 2. And then, of course, there are just 13 things here to consider. So, because, of course, you could get a 3, then a not a 3, or a 4, and then not a 4, and so on. And there's 13 of those, so that obviously cancels, and you end up with 48 over 51, which is just this, right, when it simplifies. Of course, 2 dash means not 2, just in case that wasn't 100% clear. We flip a coin continuously until this happens or this happens. Now, the key to understanding how to do this question super quickly is understanding that as soon as you hit a tail, you have lost. Because as soon as you get a tail, anywhere at all, as soon as you get a tail, to get a head at some point later, you have to go tail, head, head, in order to then try and get a third head. But of course, if you go tail, head, head, you just lose. So you can only do this by immediately doing a head, 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 which is obviously a chance of 1/8. So and that's it. It's actually quite a nice question when you just think it through very carefully and don't do too much work. This was just trial and error for me. I just drew a rectangle with sides 20 and 30, and then said, well, okay, well, how do I get, if I make a cut here, can I make these sides? Well, it actually, it took a couple of tries, but this is the setup I got in the end. 17 seemed like a good number to try and pick as the diagonal. In fact, 12 and 15 are they also good? 17 is good because it's a Pythagorean triple. It's 8 squared plus 15 squared equals 17 squared, which again is useful to know because of course you can make an 8 here if you make a 12 here, and a 15 here if you make a 15 here, and that just happens to make this perfect. Is 12 a multiple up of the 3? No, 15 is a multiple up of the 3, 4, 5. So I think that's the first one I tried, was to draw a triangle that went 6, what is it, 8, 12, 15. But that didn't quite work. So then I tried 17. 12 I don't think is the corner. Oh no, is it 5? No, 5, 12, 13 doesn't, is 12 is the shorter one. So yeah, 17 seemed like the next most obvious thing to use, and this ends up being perfect. The area of the pentagon, of course, is just 20 times 30, which is 600, minus a half times 8 times 15, which ends up being this. There's some nice ways of calculating this, I guess. But yeah, anyway, it doesn't really matter. 12, let's just draw a picture, sides A, B, and C. 12 edges, of course, means combined length is 4 lots of A because there's 4 of them, and 4 lots of C and 4 lots of B. So that's L. And then the diagonal, you can just do triple Pythagoras. It's A squared plus B squared plus C squared is D squared. And now we're looking for the surface area. Now the surface area, of course, is going to be 2 lots of AC and 2 lots of BC and 2 lots of AB and so on, I think, is the surface area of a cuboid. This looks a bit like, if you do further maths, it looks a bit like the whole roots of polynomials thing. Because if we just square all of this, we get this. And then we can just shove in this result and this result into here. This is just d squared and this is just s. And if we rearrange that, you'll end up with this if you rearrange for s equals. I think ends up being that, which is all good. Another trig question here. So root is plus or minus 4. Just to be careful. We do need to make a substitution, I guess, which I did over here. Not even sure whether this is correct. Oh, it looks vaguely correct. Just taking that range and timesing by 3/2 and then taking away pi/2. Okay, fine. So we put it in here. Root of this is plus minus 2. Now taking away 1, we either get 1 or minus 3, and then divided by 2 means either half or minus 3/2. Now minus 3/2 is minus 1.5, which is too big or too small really for sine. So this can be ignored. Sine u as a half is obviously pi/6 and 5 pi/6. And both of those are in this range, and there's nothing else I don't think that we need to look for that's in this range. So eventually, of course, when we do the substitution back, we'll end up with 2 answers. I don't actually need to work out what those are, but I think there will be 2 of them. Question 14 then. So we've got an integral which is the root of 4 minus x squared. Now, if we let like y equal this, then square both sides and rearrange, we get y squared plus x squared equals 4, which is a circle radius 2. Now, the fact that there's no plus minus here means that this curve is just the top half of that circle, so just this top half here. The minus root 4 minus x squared would be this curve down here, but that doesn't exist because we don't have it, so that's fine. So the integral of this between minus 2 and 2 will, of course, just be half of a circle radius 2, which is 2 squared times 4. Sorry, 2 squared times pi is 4 pi, divided by 2 is 2 pi. So that area there is 2 pi. Now here, by the same logic, this is just a circle radius 4. And again, it's only the top half of it. And we're only going between 0 and 4 pi, so that'll be 16 pi for the whole area, divided by 4 makes 4 pi for just this integral here. And here, now, be a bit careful with this. This doesn't look quite like the others, except you kind of can, because what you can do is you can complete the square here, just to make it look a bit more like this. Now, I hate completing the square with negatives, but I always just sort of try stuff and it works out in the end. I don't really have a system, particularly when you have nice, easy numbers. So it looks a bit like this, which I wrote like this. And now we can see that this is this same function as up here, except the x has become a minus, so that's f of minus x, and you've added in a random 2. So I think it's that transformation there. Now be careful with this, because it's easy to say, well, that's just a reflection in the y-axis because of the minus x, and then you move it left 2 because of the plus 2, but you don't. You reflect it in the y-axis, and then you move it right 2. This plus 2, after you reflect it in the y-axis, actually moves it the wrong way, or a different way to how it did it before. There's a few reasons you can justify that, but one of the nice ways of thinking about it is that when you reflect in the y-axis, you don't just reflect the curve that you're looking at, you reflect everything in the picture. So you essentially pick up this arrow at this end here and swivel it over to this end, which of course means all the positive numbers are now over here and translations work in the other direction because the numbers are working in the other direction. So yeah, this goes reflecting y, which looks the same, and then move it 2 to the right will end up looking like this. So this here is this graph here transformed like that. You can also verify this is right by just trying numbers. So like if we take this one here, when x is 0, you get 4 minus 2 squared, which is 0, and when x is 2, you get 4 minus 0, which is rooted eventually as 2. And then when x is 4, you get 4 minus 4, which is 0, and so you're back out here. So this is fine. And then we're integrating between 0 and 2, which is just a quarter of that circle, so it's going to be half of what this one was, so that's pi. This makes 5 pi in total, and so I think we have to times that by 5 and then divide it by 2, and we'll end up with our answer. So that's going to be 5i over 2, I guess, for our answer. 15, so a condition for y equals minus x is if you replace the y with minus x and you replace the x with minus y, you should end up with the same equation you had before. That is a very useful thing to know in case you ever get asked about anything about, reflecting in a line y equals minus x. So I'm just going to replace that. I'm just going to replace them like I just said. You can deal with some stuff here. I'm going to rearrange this for y, of course, by doing some multiplying. This is just basic. There's nothing complicated going on here at all. We get this. Now, the claim again is, if this graph was symmetrical in y equals minus x, then this equation should be equivalent to this equation down here. And now the only thing that we need for these to be equivalent is we need, I think, because the c and the b are in the same place, I think we just need d to equal a, which is this statement here, and we're done. So yeah, quite a useful thing to know about that. If it was in the line y equals x, that means you could just replace y with x and x with y, and it should make the equivalent statement, as you maybe suspect. Continually rolling an 8-sided die, what's the probability all the odds show up before any evens do? So okay, let's say that you roll it and you get an odd. There's a half chance of getting that. There are 4 odds out of the 8. Now, let's say that that odd number was a 3. When you get the die again and you want to roll it, you don't care whether you get another 3. That's completely irrelevant to you, because then you'll have a 3, then a 3, and you're just in the same position you were in when you rolled 1 3, right? You don't care that you've got another 3, because you can have as many, like this could go 3 3 3 3 3 3 3 forever, and then a 1 5 7, and that would still work, right? So you don't care about getting another 3. You care about getting one of the other odds, and the chance of doing that is 3 out of 7. Again, I know there are still 8 sides on the die, but I do not care about landing another 3. I care about getting the other 3 odds, 1 5 and 7. If I get one of the other 4 evens that are available, the game ends. But I don't care about hitting a 3 again, because I'm in the same situation I would have been at the start when I got my first 3. Then again, now let's say that I've rolled a 3 followed by a 1 successfully. I no longer care about rolling 3s or 1s. Those sides essentially don't exist to me anymore on the dice, because if I roll 1, I'm just in the same situation I've always been. So there are essentially only 6 sides of the dice that matter now, 2 of which are the other 2 odds that I still want. And then, of course, continue 1 over 5. All of these cancel, and you just get 1 over 70 as the answer. Kind of a cool one, I think, to think about. So this is a floor function, and this is a ceiling function. The key for these is to just draw them, right? So the floor function between 2.3 and 5.7. So between 2.3 and 3, the floor function will be 2, because it rounds it all down to 2. Then between 3 and 4, it will be 3, and between 4 and 5, it will be 4, and between 5 and 5.7, it will be 5. Now, the ceiling function between 2.3 and 3 will round up to 3. So that will be up to 3 there. So the black one is g of x. And likewise, we'll round up here, and then round up there, and then round up one more time to there. Now, if I'm doing the g of x minus f of x, that's just the area in between g of f and x and f of x, which is just this area, this area, this area, and this area, which are all just rectangles with 0.7, with 1. They're all height 1, of course. And so I can just add these together, and I'll get my area of 3.4, I think. Some people are lining up for a photo. So, okay, well, there are 12 of them, so I put 12 spaces here. The 2 red ones here are the 2 shorties, who are apparently going in the middle. So let's just call them short 1 and short 2. And now the photographer wants to line up everyone else, so they ascend upwards either side of S1 and S2. Now, firstly, I've put times by 2 here because I think I can swap those 2 over whenever I want. Now, the other people on the sides here, there are 10 of them. Now, let's just say to get these 5 standing over here, I just need to do 10 choose 5. And that puts the 5 that I've randomly chosen to be here and the other 5 to be here. Now, once they're chosen, there's only one way of lining them up because they have to be in their height order. And of course, the 10 choose 5 is doing a lot of work here because the other 5 go over here and they're going to get in their height order. So I think all I need to do is 10 choose 5 to choose the 5 that need to stand here, and everything sorts itself out. And I think I just need to times it by 2 because the 2 shorties can swap positions as well. And we'll end up, I think, with the answer of A. Last couple of questions then. Flipping a coin 7 times, what's the probability that any head has at least one adjacent head? Now, I couldn't think of an intelligent way of doing this, so I essentially just listed all of the ways possible. So we have 7 positions we can be in. This is just going to help us to do it. Now, you can't have one head because then the head couldn't be surrounded by any other heads and we'd fail immediately. So if you've got 2 heads, they have to be next to each other, right? It has to be a head, then a head next to each other in this row here, surrounded by tails. So, well, how many ways are there doing that? Well, you can put them here, next to each other, or here next to each other, or here, or here, or here, or here. There's 6 positions surrounded by tails. So, for example, head, head, tail, 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 or tail, tail, head, head, tail, tail, tail would be one way. So there's just 6 ways of doing it. Now, if you've got 3 heads, the only way to do it is to put all 3 heads next to each other, because you can't separate a head and then have 2 heads later, because then that head doesn't have anything next to it that's a head. So you've got to put them all next to each other, and again, you can put them in line here, or here, or in the position 3, 4, and 5, or 5, 4, 5, 6, or 6, or 5, 6, 7. Right? There are 5 ways of doing it. There's just one less than this because they take up one more space to do it. Now, for 4 heads, it becomes a bit more interesting. Of course, you can put all 4 heads together, and again, there'll be 4 ways of doing that. You can count across yourself. Or you could separate them out into 2 pairs of 2. Now, just to be careful here, because if we put the 2 pairs next to each other, we actually make this one, which we already counted. So, okay, to count this, I said the 2 heads could be here, followed by a tail, and then the other 2 heads could be there. So that's one way. Or the other 2 heads could be here, or the other 2 heads could be here. So that's 3 ways of doing it. So head, head, and then head, head, or head, head, or head, head. Or the first 2 could be here with the tail first, and then the next 2 could be there, having skipped this one, or here, having skipped a couple. Or finally, the first 2 heads could be there, and then you could all put the other 2 over there and start with 2 tails. So there are 6 ways of doing that. Then we get to 5. I'm just going to do the same kind of logic here. But for 5, it's kind of interesting because you can either have a pair of 2 followed by a 3, or a pair of 3 followed by a 2. So again, same kind of logic. Put the 3 heads here, space, and then 2, or space, space, and then the other 2. Or you could reverse that and put the double pair first and the triple later. So I've times that by 2 and get 6 in ways in total of doing that. For 6 heads then, you could have all 6 next to each other. There's only 2 ways of doing that. You just either put a tail first or a tail last. You could have 2 pairs of 3 heads. So it goes head, 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 tail, head, head, head. There's clearly only one way of doing that. You could have head, head, and then 4 heads next to each other like this. And again, there's only 2 ways of doing that because you can either go head, head, tail, head, 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 or the 4 heads first, then tail, then head, head. Now you can't have 3 pairs of 2 heads because then you would need too many tails to be in between them, so that doesn't work. So I think that's the 6 heads done. 7 heads, of course, just all heads. And then the sneakiest one is 0 heads, which also technically works according to the rules, and there's one way of doing that. If you count all of these up, I think you get 37 options. Of course, there are 128 in total because it's just 2 times 2 times 2 times 2 for all the choices. So we end up with D, I think. And finally, question 20 then. So if you know what this graph looks like, it's very helpful. If you've done further maths, you know that this is a hyperbolic kind of graph. So you might know it looks like this. Otherwise, a table of values kind of gets it done. Likewise, this one similarly, if you want to do that. Otherwise, for this one, you can just think, well, okay, if you just swap the x, in this first equation, if you swap the x and the y over, you get y squared minus x squared equals 1, which you could then times everything by minus 1 to get this thing here. So, okay, well, this is the y-axis, this is the x-axis. So if you swap those over, the graph will end up looking like this, right? So essentially, I'm just turning it 90 degrees, and it ends up being like that. So that's my logic for why that graph looks like this. Of course, these are just a bunch of lines. This one has gradient 1, y-intercept 2 plus root 3, which is roughly up here somewhere. And likewise, this one gradient minus 1, I guess, because of this minus. And so you end up with a square like this. So you have to be careful to kind of draw those reasonably. I mean, my drawing is pretty terrible, but I think it's just about going to work. Now, what's the area of the enclosed region? So they're asking for this area here, this kind of cross shape in here. Now, we're apparently given that the area between x squared minus y squared equals 1 and x equals 2, which is here, is equal to that thing there. Now, that there, now, this area here, but x equals 2 is this line here. So this area here is all of this thing here. So I'm going to halve that down and say that's just this area. So half of this, which is of course root 3 minus a half log 2 plus root 3, is this thing here. And I'll use that in a second. So okay, now this is just a triangle. So that shouldn't be too hard to work out. This is obviously 2 plus root 3, and this is 2 plus root 3, just based on how these lines are working. So the area of, I mean, we can do a couple of things here. Firstly, I think I just said, well, let's focus on a quarter of this first. Because I think my plan is just to work out this whole triangle, take away this area and this area, which will of course be the same thing because of symmetry. Take away this triangle and this triangle, that will give me this area here, then times it by 4. So this triangle here is just a half times 2 plus root 3 times 2 plus root 3, which is, I mean, it just ends up being that. Just because you get 4 plus 3, which is 7, then halved it, and then 4 root 3 in the middle, halved it. So it's going to be this, and then this triangle here. Now, when you put in x is 2 into this red curve, which was this one, you just get 4 minus y squared equals 1, so y equals root 3. So this must be at root 3, which means this triangle, because this is at 2 and this is 2 plus root 3, this is also root 3. So root 3 times root 3 over 2 is just 3 over 2. So I think we're pretty much done here. We can just take the whole triangle, which is this, take away this, take away another copy of it. So take away 2 lots of this, essentially. Half, I remember we did. I could have not halved it and then not doubled it or whatever. And then also take away this 3 over 2, which I've added in. Essentially, I've added these two things together first in this bracket, and then doubled them to get these 2 bits in total, and then taking them away from the big triangle is just what this math says. There were plenty of ways you could have gone about it. And the last thing I have to do is times that by 4, because there are 4 of these areas to think about in total, and we end up with the answer of F.